Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Miller, and I'll be your host for today's presentation on 3D plasma simulations for PECVD, sputtering, etching, and more in Ansys Charge Plus. Please use the Q&A feature to submit any questions you have during the webinar. At the end, we will address any submitted questions. Our speaker for today is Kevin Miranda. Kevin is a senior scientist at EMA and the lead product manager of Ansys EMC Plus and Ansys Charge Plus. His expertise is in atmospheric electricity physics, elementary particle physics, and computational physics. Through webinars or at conferences, he gives regular updates on the development progress of the two software solutions. He is very excited to discuss this update on the latest big development to the EMA physics solvers. Without further delay, I give you Kevin.
Thank you, Matt. Good to have everybody here today. Very excited to show you the capabilities that we have and also the newest updates in terms of features and validation that we've done this summer. The topic is very focused on 3D plasma simulations for the manufacturing industry, both for semiconductors but other processes. But as you'll see later on in this presentation, a lot of this technology can be used for many, many different types of applications. So I'll be introducing EMA, then I'll go through some of those plasma applications, various plasma applications and Ansys Charge Plus. And I will go through the physics fundamentals for the modules that are relevant to the semiconductor industry, go a little bit through our development history over the past few years and how we've progressed in terms of the capability, some of the new key features that really brought a breakthrough in terms of the stability of the solver and the technology as a whole to be able to solve these problems that we've developed this summer, some of the latest validation update using these key features, and then some additional demonstrations related kind of back to the second bullet point that you see here, which is the general applications of the tool. So EMA stands for Electromagnetic Applications. You can get more information about us at ema3d.com. We have about 60 employees, and our headquarters is in Denver, Colorado. That's where I am right now. We are very active with SBIRs and STTR contracts and the space and defense industry, and we work across across many different industries as well. We have an expertise in consulting, simulation, and measurement, and we work with companies for services around the world. We specialize in EMI, EMC, EMP, RFI, antenna, radar, spacecraft charging, lightning effects, and then we also do a lot of complex simulation measurement combinations. And then I added 2 bullet points down here where we do specialize in the development of engineering physics software and in multiphysics specifically for plasma modeling. So we do a lot of consulting. We do provide services. So if you have some problems in your group, in your company that you need help to solve, or if you want to use some of the solutions that you're seeing today and have EMA help develop a workflow or solve a problem for you using these solutions, we are here to do that. We serve as experts in EMI, EMC across many different industries. We work a lot on first-of-a-kind scenarios for solving problems that have never been solved problems. And we also develop new capabilities specifically for solving problems that haven't been done before. So there's a lot of resources at EMA that you can leverage. We also have cleared employees for dealing with maybe secured information, things like that. So we can definitely work with you to build NDAs and build a relationship in terms of handling proprietary information. EMA is a technology partner of Ansys. So we developed the solution that you'll see today, and Ansys EMC Plus and Ansys Charge Plus. and Ansys distributes those solutions. So we work with them internally. We have an application engineering team. We have our developers at EMA, and we partner with Ansys to distribute the solution. Ansys Charge Plus is our charging and discharging modeling solution. Ansys EMC Plus is our platform level EMC modeling. So you can see here on the left that EMC Plus is very focused on solving full wave electromagnetics across large platforms by using a finite difference time domain solution. We also model the cables inside the system, which are very important. Just as a little side note, when we are talking about plasma chambers for the manufacturing processes, these chambers are hooked up to power supplies. The plasmas are going to be sensitive to external radiation environments. The plasmas themselves are going to generate electromagnetic fields and radiate those across a full room and might create interference across a system that is sensitive in terms of electronics across that room. The EMC Plus solution is very well suited to be able to solve those large scale electromagnetics. We also solve electromagnetics on PCBs because we want to be able to integrate and do a full solution at once by modeling small scale and large scales at the same time. So if you have a component, a PCB that is sensitive near your plasma chamber, for example, and you want to understand how it responds with the power supply being present and things like that, we can do that analysis. Ansys Charge Plus is our solution for modeling the plasma. And at its heart, you need an electromagnetic solver to be able to do that because the plasma and the charge particles are going to respond to these electromagnetic fields. One of the first applications, as you'll see in this presentation, was leveraging these solutions that we now use for semiconductor manufacturing for space radiation. So in space, you have to deal with a satellite that can't be grounded. It has to interact with that plasma that is present in space, and that will lead to the spacecraft charging concerns that arise in the space and defense industry. A lot of the technology for understanding how plasma responds also helps us model how plasma gets generated or how plasma dissipates. And that's some of the other workflows that we can tackle, such as ESDs or arc extinction, by being able to model, for example, recombination rates of a plasma or ionization rates of a plasma, coupled with the electromagnetic problem around it. And then finally, a lot of this technology can be used, as you'll see, for the semiconductor plasma industry, and this is the discussion that we're having today in a lot of details. So plasma application specifically from Ansys Charge Plus, we are going to see that it's applicable across many different industries. So you can do high voltage systems, understanding creepage and clearance issues, breakdown voltages. You can model high current switches as well, a lot of space radiation effects, especially the one we just discussed for surface charging concerns when the plasma is higher densities than what you would get from, for example, cosmic ray radiation, modeling particle beams, modeling RF amplifiers, and also in the packaging industry, understanding how you can do various deposition or ionization of air in various ways, modeling X-rays and how those are generated, for example, from an electron gun in a medical device. And then we have the whole application of RF plasma, specifically for semiconductor manufacturing, which is what we'll dive into a lot of depth today. Electrical discharge machining also uses arcs to be able to do their work. And so modeling that process requires the tools that we'll see today. Vacuum and rarefied gas systems. So if you are dealing with really places where fluid solvers are not valid anymore, you can use the technology in Charge Plus to do that, to be able to solve for the flow of molecules or particles inside a system when the pressures are very low. In the electronics industry, you can use discharges for ionic wind, for example. These are some of the topics that have come our way in the past. And then also understanding how to heat up a gas using plasma. So you have electromagnetic waves from a waveguide, for example, and that can lead to the heating of a gas. And we can solve that for example, for torches or other applications. So for the semiconductor industry specifically, we have these chambers that are present. These chambers is where we generate a gas. Typically, the application requires a very specific gas, and the design and refinement of that gas is dependent on the application and on the optimization of the process. The gas is going to be generated with an RF source, and it's going to create a plasma that will interact with the surface of the wafers, for example, or of the surface of the device or the component that you want to interact with. And at that surface, there's a lot that can happen depending on what you're trying to do. You can carve out material, you can sputter material, you can deposit material, right? But at the end of the day, what you need to do is model the plasma in 3D inside the chamber to be able to properly understand how those ions are going to interact with the surface. To properly model the 3D simulation, the 3D distribution of the plasma, you need to leverage the technology that we'll be discussing today for electromagnetics and things like that. Some of the things that we want to be able to do is help the industry with understanding how to optimize the deposition process, how to make sure homogeneity is present, how to make sure quality is there. We want to also improve the speed of the process. We want to use simulation to see how to do that. And also we want to be able to take existing devices to the next level and change the gas that it's running with, things like that, see how it responds to changing the plasma capabilities that are within the system. And then ultimately, what we are able to extract from a simulation is the velocity of the radicals or the ions near the surface of the device that needs to be under test to properly understand how the chemical processes interact at the surface. That is where etching, sputtering, and deposition comes in. The tool that we're talking about today, Ansys Charge Plus, really gives us all this information of the plasma in 3D. And then there are a lot of tools that can be leveraged afterwards to be able to extract information on the etching process itself. So why is it so hard to model these plasmas in 3D? Well, we are dealing with different regimes depending on the type of plasma. When the pressure is too low, tools like CFD are no longer valid. So we break continuity. And then when things are too high in terms of pressure, typically other tools that we use for low pressure environments are too computationally intensive. So particle and cell, this is something you'll hear me talk about a lot today, PIC, is very difficult to use when the pressures are too high because the plasma has a very fine Debye length, which is how the charged particles respond to one another and how fields are being screened by the plasma. And so for us to resolve that accurately, we need to have a very fine mesh, and so the tools become very computationally intensive. So as you'll see in Charge, we've developed various ways to be able to handle these type of concerns. The other concern is that plasma recipes are very complex and very proprietary. And so they require many species and many reactions that just adds to the complexity of the problem. So there are simulation tools out there that are present, but they're not computationally efficient. It makes it very hard to get a very accurate solution, especially with those problems that we want to solve in 3D on complex simulation, on complex designs of chambers, for example. And then we have to really understand that multiphysics requires multiple timescales as well. And so that makes things very complex in terms of handling RF power versus handling the motion of an electron in a certain system, or even the scale of the reaction, or the much longer timescales, which is the flow of the gas injection inside the system, or the deposition process. So we've developed methods in Charge to be able to do that. And we think we have a solution that is meant to be able to help you out for solving these problems. So the key in terms of kind of outlining the system here is that we have a user interface that is Ansys Discovery. I'll talk a little bit more about this. We have the ability to use hybrid solver capabilities by modeling both PIC and CFD at the same time. This allows us to solve, for example, the gas injection inside the chamber, and I'll also show some more details about that later on. And then we have integration across Ansys, which allows us to solve and use solutions for various types of problems. So for example, if you have a magnetron and you want to model the magnetic fields from a magnet, you can do that very well in Maxwell, and we can import that information in our tool to understand how the plasma responds to that information. And then another very key ability is to be able to speed up these simulations. We've added various models like plasma sheath models and also some implicitization schemes to be able to get the plasma to reach steady state over time, even at higher densities. And so you see that we have some various adaptive meshes that we can add near the surfaces that will change the resolution of the mesh and help us model the sheath properly. So there's a lot of advantage, like key numerical capabilities that are present in the tool that are there to solve a lot of these complex problems. So at the heart of the tool, we have these four solvers specifically for the manufacturing process and the deposition process. All four need to come together to be able to get the solution to work properly. The first thing is the electrodynamics. We have RF sources, we have antennas, we have magnetic and electric fields. There are currents in the system. We need to be able to solve for the proper electromagnetic solution associated to this problem. The next is the particle in cell. This is to be able to solve for low pressure, like environments or even higher pressure environments as well, but really monitoring and tracking electrons and ions flowing from one location to another in a system and how they interact with the surfaces of the model. CFD is also present, so this is used to handle higher density regimes. So we don't have an automatic way to convert a PIC particle to a CFD fluid or a gas, but you can actually initialize the simulation in a state that allows you to leverage CFD, especially when you know that your ions are going to be at higher density, and that helps us solve these problems that make it very hard for PIC to solve when the densities are very high and the sheath and the mesh needs to be very small for PIC to accurately solve that problem. And that helps us also speed up the solutions. And then the reaction solver is there to be able to understand how the gas and the plasma is being generated or dissipated, right? So we need to understand the energy of these electrons and ions that are present to be able to and their densities to properly solve for their change in densities and change in energies over time. And this is key because we need to be able to get the right levels of ionization, so we know exactly how many electrons are reaching the surface of the semiconductor device that we're trying to manufacture. Again, a lot of integration across the Ansys portfolio. As you'll see, we use the discovery interface to be able to set up the problems, mesh the problems, and also visualize the data. We are coupling with other tools like materials database at Ansys, Chemkin as well, Fluent, and also HFSS and Maxwell, as we just saw. And then we have integrations also for other heavier particles and larger particles from Ansys Rocky. So there's various ways to take information from the Ansys portfolio and add it to our simulation. So this is the user interface that we have, Ansys Discovery. It allows us to import a CAD. You can design the CAD in here, and then you can go to the Charge tab, which is available at the top in the ribbon. And then you can select our plasma library, as we just saw, and it will generate all the species, in this case for humid air, and we can assign these species to the vacuum inside the chamber. And you can change the densities, change the temperature, change the plasma environment, and you can save that new plasma as part of this library. So we ship with nitrogen and argon gases. We'll be adding some in the future. And then you can see here that we can also edit all the reactions within the user interface. So this is us setting up a problem for monitoring how air can flow inside the system, for example. And then if you want to add an RF source, we can do this. In this case, this is an example of the same chamber, that same vacuum, where we generated an argon gas, and we are able to apply a signal to the system, in this case, an RF signal. And we have also an emission model that is present and available from one of the tools up there to be able to understand if electrons are going to be emitted when the fields are too high. So in this case, we reached values for electromagnetic fields that were high enough to create E-field emission and generate electrons inside the system. But this is really showcasing the ability to visualize the data in 3D and the results of the simulation using the graphical user interface inside Discovery and the visualization arc on the right. So you can change between the density, the temperature, you can do cut planes and visualize the data in 3D all within the same workflow. So physics fundamentals, I think I just introduced the overview on how each of these solvers kind of integrate together and what their purpose is, but let me go into a little bit more details on what we want to do. So the time domain electrodynamics is really meant to drive the potentials and the fields in the system and also understand the fields generated by the plasma. The PEC is meant to be able to track the energy and the density of the particles and their kinematic and dynamic around the system. It can be for electrons and ions. And then the CFD solution is there also responding to electromagnetic fields and generating fields. So it's also coupled to the electromagnetic solver, and it's used to be able to solve gases that are at higher densities, for example, in a discharge, or even like an air discharge at sea level, things like that, where the densities are much higher. CFD is very useful. Or if we want to understand how the neutrals that are present, how those which typically have a much higher density move at a larger time scale inside the system around where the plasma is being generated, for example, or the heat imparted by the ions onto those neutrals. We can use CFD for that. And then the reaction solver is present to solve for the changes in densities and temperatures of the system through scattering cross-section data. And we can also solve for some of the surface reactions as well. So electrodynamics in the finite-element method, you can see here solving for the fields from the potential. The potential formalism that you see here accounts for what we call the space charge distribution. This is key for these problems because as the electrons and ions redistribute in the system, they're going to generate electromagnetic fields, and that basically space charge distribution needs to be accounted for in the electromagnetic fields. This is how the plasma screens the fields applied to the system and reaches a steady state. So we can capture that both in the quasi-static state or in a full wave formalism. It's coupled to the PEC. So the particle in cell is a tool that is used to track electrons and ions. We don't track 10 to the 18 electrons. It's too computationally intensive. So we track what we call macro particles. These macro particles are moving throughout the mesh in 3D, and they are mapped onto the mesh using this octree spatial partitioning tool. Each macro particle, we calculate the Lorentz force associated to them based on the fields in the system at each time step, and we can solve for how they redistribute based on those fields. We have mass and energy conserving methods, as you'll see later, that are key to make sure that these particles exchange energy and are tracked properly inside the system, and various boundary conditions as well. As electrons and ions redistribute, they have a space charge with respect to the grounded surfaces in the system or with respect to the particles themselves. And so they create fields that we need to account for. And as you saw, we can track that in the electromagnetic solver as an additional source term. When we use the CFD, we do something very similar, but we solve for Navier-Stokes equation with a force term that is present from Lorentz force as well. And just like we do for PEC, we also solve for the space charge due to the fluid in the system, associated to each fluid species in the system. And so you can actually co-simulate the PEC and the fluid at the same time, both contributing to the space charge distribution and both interacting with one another. So a species in fluid may interact with a species in PEC and so on. And this is done through our reaction solver. It's called PEC MCC, but also accounts for the fluid formalism. And we can model any of the reactions that you want in this solver. So how do you define a plasma? The plasma is not just its densities and its species, it's also its reactions. And typically you source those from electron cross-section information. So this is what it looks like for a nitrogen molecule. It's very complicated because you can excite nitrogen, you can ionize it, you can break it down into nitrogen ions as well. And then there is elastic collisions that need to be captured. And so as you saw in the previous user interface demonstration, when we model air, we have to also capture the ions and the excited states of the system to properly understand how all the energy is being exchanged between each of the ions in a discharge. The key as well is that there's a lot of different timescales to worry about. You have the neutrals that can flow with a certain bias in the chamber, and at the same time, you have to worry about an electron moving around very quickly inside the sheath of the plasma. And so how do we do that in Ansys Charge Plus? We have this scheme here that you see where the PIC will run iterations on its own timescales that are defined automatically by the solver. Then we update the boundary conditions and the electromagnetic fields from the applied voltage. And then we can have a timescale that we call the RF cycle timescale that allows us to run through a set of cycles, let's say 10 or 100 cycles, and extract the information and calculate averages over those cycles. And then we can accelerate even further through, let's say, a macro scale time step to be able to understand how the fluid flows through the system and how deposition happens on a much longer time scale based on some extrapolation that we can do at each RF cycle steady state that we get in the system. So a lot of this is automatic in the solver. The information that you set in the user interface is the size of the RF cycle and the acceleration time step that you want to take. But the PIC will iterate to be able to reach its steady state and run these simulations efficiently. So let me go through some of the development history for the tool. In 2021, we already had the particle and cell solver for electron and ions, no reaction solver. This was for electrons and protons and also ions. You could model multiple species, and it was really meant for understanding spacecraft charging and how these particles interact with the surface of a satellite. In this case, you can see we have a bias velocity of the spacecraft through the plasma. It creates a wake, and you can see the sheath of the electrons and also the wake behind the spacecraft. So here, the sizes are very large, and so because the densities are so low as well, the plasma sheaths are much larger, and you can resolve it with numerical methods and meshes that are not that complicated. But when you start increasing the density, then you have to refine your mesh, and it makes the problem even harder, as we know, for these plasma chambers. The key for this application in the space and defense industry was to understand the risk of electrostatic discharge across surfaces that are charging differently in the system as they interact with the plasma. So in 23R1, we started making some progress in terms of tackling higher density plasmas. We introduced the CFD solution and the reactions that start becoming very important when the densities increase. So on the left, we can see the response of ions in CFD to the electromagnetic forces that are being applied as a RF source on the electrodes of a chamber. So this is the inside of a chamber. We have the wafer on the bottom, and we have a pulsed signal on the top that applies a strong voltage, and that creates a force on the oxygen ions in the system. And then we started interacting with Chemkin to be able to solve for reactions, because when you don't have reactions and you saw the space application, the electrons can move around a lot, and a chamber without reactions or air without reactions allows for free electrons to move around. The mean free path is gigantic, and so you get a lot of dynamics. But when you start including reactions, now the electrons are going to interact with the gas. The temperatures are much lower, and you're going to get some behavior that is very important to capture if you want to properly solve for the ionization levels in your system. Then in a couple months later, we started developing new techniques to be able to resolve the sheath, especially when you're dealing with such higher densities. So we were able to both do full PIC simulation and hybrid simulation using fluid and PIC, and still resolve the sheath in very fine mesh elements. So we actually have the solver automatically create and extrude the mesh near the surfaces where we want to resolve the sheath. We call it automatic boundary layers or adaptive mesh, and that helps us resolve the sheath that you can see in the system, and it is coupled to the unstructured mesh inside the vacuum that is here. And this sheath will change the potential. So instead of having this potential that you apply to the surface that will drive the fields in the system, you have to account for also the distribution of the plasma near that surface to properly solve for the potentials. So that those tools were developed and key for various applications that require higher density plasmas. Then we started modeling with these capabilities the RF chamber with lower gas densities here, in this case 1e11, so near vacuum, and we're able to see the sheath form near the electrode in this adaptive mesh region with the density of the plasma changing over time and reaching a steady state. On the right, you can see the 3D simulation responding to this. At those densities, the Debye length is pretty high, so you're not actually worried about having a mesh that is very, very fine to be able to solve this problem properly. So in this case, we were able to run about over 10,000 cycles in about 3 days with the mesh resolution that we used here at those densities. So we can already solve in Charge Plus a couple years ago the near vacuum environments or even like lower density gas environments for any gases using the reaction solver that we have. The question is what happens when you start reaching higher densities. That's where we have to develop a couple more capabilities as well. The validation progress for the tool is also something that we can track through this year. I think earlier this year, we were able to present how the tool responds at those higher densities using the fluid solver and also using the PEC simulation. So one of the validation cases that we have is against this paper here from Buff and Pitchford. And we have what we call the GEC reactor. This is a big standard in the RF plasma community, especially for semiconductor applications. And we can see that the distribution of the plasma across the chamber vertically here between the two electrodes is what is very important, as well as the radial distribution. And we'll be able to see the radial distribution on the top here inside the chamber, as well as the axial distribution of the plasma. And so making sure that we get the levels that are expected in terms of the density of the electrons and its distribution will tell us that the electromagnetic solver is working well, the reaction solver is working well, that we're able to solve for the sheath properly in the system and get the expected level of ionization. And so here in earlier this year, we were able to see that we're able to get the proper ionization levels using the reaction solver that we have in the tool. The other things that we released earlier this year in 2024 R1, which is January or even the end of last year, is a lot of emission models for generating electrons inside the system. So we've developed the thermionic emission or the Schottky emission process. Secondary emission models we've had for a long time. We needed it for the spacecraft charging applications, but here we also have them if you are worried about secondary emission inside the chamber near the cathodes. And then field emission, let's say the fields get very high, so this is cold emission. These are all important for various applications like discharge models, but also electron gun models. So these were also things that were developed. So now I'm going to go into discussing the key features for the RF plasma application that we've worked on very hard this year. The first thing is modeling the sheath in the system using a 1D sheath model. So it's a subcell sheath algorithm near the surface. And the reason we need this is, as we've just talked about, when the densities get very high, the sheath gets very small, the Debye length gets very small. So how can we go beyond this problem and be able to solve this problem in a reasonable amount of time is by using subcell algorithms so that we don't have to resolve these explicitly. And so we have two subcell algorithms. We have an analytic sheath and a kinematic sheath that we've developed in the system that helps us solve for the distributions of ions and electrons near the surface without actually creating a mesh for it. And that helps us solve accurately for the temperature and the potentials inside the system. The kinematic sheath is expected to be much more accurate, as we can basically use a 1D PIC model to solve for the distribution of electrons along the normal vector from that surface. And we can also implement surface reactions with the kinematic solver. So if we want to understand how an ion interacts with the surface and generates more ions or a byproduct of the reaction, we can add these as part of the 1D sheath model. Other improvements were stability improvements. So we have what we call EC-SIM, energy conserving semi-implicitization. This is to help us solve this problem of numerical heating that occurs when the Debye length is not resolved properly. So without implicitization, you can see that when you initialize just a plasma in a cube, the temperatures are going to diverge. The electrons are going to really move around and just get heated for numerical reasons. And so we need the technology to be able to bypass that problem. And so this is part of the tool. We've developed implicitization schemes inside Charge to be able to keep the plasma stables over a long period of time. And we've used this for plasmas up to 1e to the 18, for example, for PIC. So that helps us solve and keep a mesh size that is very large. I think we've used a mesh size that is 100 to 1,000 times larger than the Debye length and still are able to keep the plasma stable. We've also developed new post-processing capabilities, like being able to monitor the electron energy distribution function. And here, this is very powerful because when we want to understand how the plasma responds or what Maxwellian distribution, for example, it represents after a set of cycles to make sure that we reach steady state properly, then we can do this. Here, we're looking at the change of the plasma distribution over time of the electron energy. And this tells us that we're reaching the expected plasma and an actual plasma that is stable following a distribution that we expect from the physics. Other tricks that we've developed over the summer is the ability to create slices of the geometry. So we've seen the chamber, and here we actually created a slice in the CAD, and we just mesh the slice, and that reduces the amount of elements because we don't have to solve this problem in 3D. We're effectively now solving the problem in 2D. You can use a tet mesh to resolve a lot of small features along that slice, especially for that cross section, and still solve for the problem and the distribution of the densities and potentials inside the system. In this case, we're able to solve the GEC reactor in 12 hours on the desktop using a full PIC simulation, using EC-SIM and the sheath models for 0.25 torr. So it really helps us get to these problems that are typically very hard to solve in a reasonable amount of time. We've also are working on the SPICE circuit modeling for boundary conditions where we can couple to a circuit solver the boundary of the system or an antenna, for example. This is helping us with much broader applications than just setting a current or a voltage source near a surface. And it also will be responsive to the potentials generated by the sheath so that you can keep adjusting the power in the system throughout your simulation based on the sheath and the currents flowing through the chamber. So here are some of the latest validation updates that we have with the tool using all this technology that we talked about. So you can see here our structured mesh that we've used for these applications earlier this year. We are able to resolve, again, very well the sheath, very well the mesh in this case, but the Debye length for this system is much smaller than the resolution that we're seeing here for this grid. And so our goal is to reproduce the potential and density distributions that are in some of the literature. The interesting part is that the electron density and the ion densities are a result of the reaction solver. And then the potentials are a result of the space charge distribution being properly calculated once we reach steady state. So the value that we see for the potential is very important. Here in the electron density as well, we're able to see the two peaks that we expect near the edge of the electrodes. We're able to see that we reach steady state, and we're running through, in this case, 100 RF cycles in the system. So this is a full PIC simulation at 0.25 torr. It was actually run on a laptop. With this structured mesh, we reduced the problem space to 10,000 mesh elements. You can now also use this 2D slice method that I just mentioned. And this was ran in 12 hours for 100 cycles, which was enough to reach steady state in this simulation. And we can see the peak in the potentials near the electrodes. We can see the sheath being formed as we would expect for the ions and electrons. This is also using the 1D sheath model in addition to EC-SIM. And we can monitor the ion, argon, and electron densities that are expected to be generated in this simulation. So this is just going through the checklist of things that we want to make sure we properly validate. We're reaching steady state for the plasma simulation. We're getting the proper distribution of the plasma as a function of radial distribution and axial distribution, things that we've done in the past, but we're still able to do that more efficiently now with the new solution. Monitoring the electron energy distribution and also the potential distribution to make sure the values are matching. So we're matching an amplitude here around 38 volts in the space charge distribution from the plasma reaching a steady state. We expect even more speed up from using CFD for the ions. This was a full pick, and also some future performance optimization that is coming in the next couple of months. We should be able to get even 2 to 5 times faster with those accelerations. So just to wrap up the discussion today and show you how to use this tool with other type of workflows and other applications. In this case, if you want to import the fields from HFSS, for example, instead of driving them with a source and charge, you can do that. The fields are generated by a waveguide, and we can pass those electromagnetic fields to Charge Plus, which will generate the electron distribution that you see on the left and the associated deposition with the electrons interacting with the surface. So if you want to model a gas in that way using fields from another source in Ansys, you can do that. That helps us. We can actually convert the frequency domain data to time domain data directly into Charge Plus. Another application is if you have magnets for a magnetron, for sputtering, for example, and you want to understand how they affect the behavior of the electrons in the system, you can actually model those electromagnetic fields in Maxwell, well, the magnetic fields specifically from the magnets. Maxwell has a great workflow to model magnets, and we can import those magnetic fields directly inside the system. So here you can see the magnets in the 3D geometry in Charge Plus. And then we map that onto the mesh that we use to solve for the plasma distribution in the system. And you can see the electromagnetic fields on the bottom right from those fields. So you can add that in addition to an RF source, for example, and you can combine all these sources together to understand how the plasma responds. We can also solve for B fields directly in the tool, especially if they're time domain. You can drive antennas. So this is kind of a 3D contour plot, a cut plane of the magnetic field distribution associated to an antenna inside the chamber. You can add those coils inside the tool by just drawing it as a geometry, assigning it a conductor material, and then driving it with a current source that will then generate magnetic fields that will affect the plasma distribution in the system. Basically just taking the CAD that you see on the left here and adding the antenna up top in the system instead of adding the magnet at the bottom here. And the other thing is leveraging the CFD solution as a standalone solution or even as a predecessor to or prequel to modeling the RF discharge, understanding how the plasma, the gas gets filled inside the chamber based on some changes in the CAD. So you can fill some of the shower head holes, for example, understand how things reach steady state or how the gas looks like inside the system, and then light up the system with the electromagnetic sources to be able to generate the plasma. We typically do this at this time in 2 steps because the timescales are very different as we've seen in the past, but ultimately you'd be able to solve everything together if needed. Electron gun simulations and modeling electron interactions with gases. So this is important if you want to generate ions in various ways. We really have high fidelity models of electron flood guns or electron beams and how they get generated using the thermionic emission. So we monitor the space charge distribution from the beam itself, from the ions that could be generated if there is a gas in which those electrons are being imparted. And if we need to take that to the next level to model X-rays, we can use other tools in Charge Plus, like the like the radiation transport tool to be able to solve for how high energy electrons are going to interact with tungsten, for example. So there's various ways for us to couple these workflows and really tackle these type of solutions. One of the other discussions that we've had in the past was electron ionic wind. So you have a spark that is generated from a tiny little needle, and those electrons are the ions are getting captured by a ring that is grounded in the system, but there is momentum transfer to the neutrals in the system that will generate basically wind, right? And so with a very small corona discharge, you can create wind inside a very small confined space. And so we can solve for this momentum transfer and for the velocity of neutrals using the reaction solver that we have as well. And then I think this is one of my last ones, is really modeling discharges on a different level. We saw an RF discharge, but we can also model DC discharges. So if you want to just ramp up the voltages until you get a spark and solve for the breakdown voltage, we can do that in the tool as well. And this is using the air chemistry that we showed at the beginning of the simulation. And those ions and electrons are being affected by an external magnetic field that is shifting the spark between the top electrode and the bottom electrode over time. And so that extends the spark length and will change the resistance of the arc that is being generated in the system. And we're using the same technology here, the PIC, CFD, EM, and reaction solver. All of them are working together for this application as well. We can get the proper breakdown voltages that change based on the gap, on the pressure, things like that. And we can do this for any gases because as long as you have the electron cross-section data, we can solve for that problem. So this is it for my discussion. I will leave you with this kind of summary of the capability. If you want to inquire about more information related to the software or the services, definitely go to ema3d.com. We can help out and help you solve some of your complex problems. Thank you for listening.
Okay, thank you, Kevin, for that really informative presentation. Let's review the questions that we received during your presentation. By the way, if you've not already submitted a question, there is a Q&A button in the Teams interface. So just click on that and it will allow you to submit a question. So the first question is, how do I evaluate the software? I assume they're wanting to evaluate the Ansys Charge Plus product.
Yeah, so the best way is to reach out to Ansys or your account manager. Your company will have access to that information and who your representative is at Ansys, and they will be able to issue an evaluation license for the tool if the company doesn't have access to it already. And from there, we have typically the ability to try the tool for 30 to 60 days and be able to run some of these workflows that you see here today.
Okay, thank you, Kevin. Next question. Can EMA help with services related to plasma applications that contain intellectual property?
Yes, so EMA, as I think introduced in the beginning, we specialize in consulting services for various applications. In the space and defense industry, we have people that are here at EMA cleared to be able to handle top secret or secret problems, but also just in general, being able to deal with IP. EMA is very well versed and able to turn around NDAs very quickly. So if you want to solve a problem very specific to you that you don't want to be, that you're worried would be shared with competitors or things like that, this wouldn't happen here. EMA really is able to contribute to that. I don't know if you have anything else to say on that, Matt. But
yeah, no, I think that's a good summary. I mean, we work with our customers, and different customers have different requirements for how we handle data, and we comply with whatever those requirements are. So, yeah, I think that's a really good answer.
Perfect.
Next question. I'm not sure if this was related to the last one or not. Do you publish or present some of these results at conferences?
So when we do validations of the software or we do testing related to validating the software, if we do get time, we do publish some of those results. And we have actually one of my colleagues that went to the GEC conference last month and presented some of these results as well to the academia and industries that were present at that conference. So depending on the topic, and especially if it's not proprietary, then sometimes, yeah, we are able to bring this to the community and give feedback from the community on how this tool works.
Okay, thank you. Let's see, another question here. For a chamber electrode to which the RF power is supplied, is it possible to observe its impedance versus time as the plasma ignites?
Yeah, that's a great question. Yes, so we can monitor the potentials associated to the electrode by modeling the electrode itself as a conductor. And then we can see based on the interactions of the plasma species with that electrode, how the electrode charges up or changes in terms of response to the electromagnetic field. The additional thing I want to say is we're also going to be able to use that circuit solver to be able to get more information about the impedance of the system as a response to the plasma forming. So there's various ways for us to solve that problem. But yes, we can get that information.
Okay. Another question, for ESD modeling of a multi-layer surface, do we need the DAC model of each layer, or the outer layer CAD model would be enough? I think that when they said DAC, that's a spelling mistake. I think it's supposed to say CAD. So let me read that again. For ESD modeling of a multi-layer surface, do we need the CAD model of each layer, or the outer layer CAD model would be enough?
I think for thin surfaces, we have various workflows. Ideally, you can just define the thickness and the type of material and do the stack up in the UI, and the solver generates that stack up automatically. The other way at this time in the user interface, I think, would be to actually resolve each thin layer like you are proposing, and then define an extrusion or thickness, material property associated to each layers. So we are definitely working on subcell algorithms for those surface materials so that you don't have to resolve them explicitly in the mesh. I think we have some of those capabilities in the solver, but for now in the user interface, you have to resolve the CAD.
Okay, thank you. Next question. How do you simulate etching or deposition once you have the 3D plasma distribution?
Yeah, so that's a good question. So on the bottom right here, you can see the electrons density. We also have the proton density, and we monitor those near the surface through the sheath. So that information is the information that you need to be able to solve for the proper surface reactions. We have an analytical surface reaction model, or you can get the surface reactions from Chemkin as well that you may have defined there. And in the future, we are working for the roadmap for 2025. We are working on being able to solve for reactions directly inside the tool. So these would be reactions associated to the bulk plasma. If you want to model much smaller behaviors and features, then you can extract the information that you get from this simulation about the ion densities and velocities and momentums at the surface and pass them to another tool, for example, a synopsis tool that can actually model the etching process. And as an initial condition, instead of having a fixed momentum and density, you would have the information from the simulation that we solve here.
All right. Here's a question that I can answer. Will the recording of this webinar be available somewhere? The answer is yes. If you go to the ema3d.com website, and then there's a link at the top for latest news, you'll see our webinar series listed there. It'll take a few days for us to get this posted, but we will also email a link to the recording to everyone that registered for the webinar. So yes, you will be able to access it following this meeting today. Okay, well, I think that's all of the questions. We still have a few minutes if we get any last second questions here. Otherwise, I think we're going to wrap it up. Kevin, anything you want to say before we conclude the webinar?
No, I think I shared enough information for today. Thank you.
Okay, well, thank you. Um, let's see, so you will, as I said a moment ago, you'll be receiving an email from us with a link to the recording of this presentation. If you have any questions about a particular section of interest to you, please feel free to reach out through the ema3d.com website or through email directly to us. Next up in the EMA Solving Electromagnetic Challenges webinar series is Accelerating Electromagnetic Simulations with Machine Learning, an Introduction to EMA 3D Connect. This is going to occur on November 13th, and we're really excited about this. Our team at EMA has done some pretty amazing things with AI and ML, and we're really excited to share that with you. Thank you for your time and attention, and we hope you have a great rest of your day.